Hello, ESE 523. I'm Andy Myers, and today I will be talking about Xmon qubits. First, I will discuss similar qubit architectures and provide a historical overview of Xmon qubits. Then, I will talk about how Xmon qubits operate and the current state of the art. Finally, I will go over some future challenges for research of this qubit architecture. Whenever we talk about qubit architectures, it is helpful to frame things in terms of the DiVincenzo criteria. There are fundamental trade-offs in coherence, coupling, and control of qubits, which is why it is difficult to develop architectures that meet all DiVincenzo criteria at once. The two criteria most relevant to our discussion of Xmon qubits are scalability and coherence. Superconducting qubits are made of macroscopic superconducting circuits, which are an easy architecture to scale. However, these qubits are sensitive to charge fluctuations, making them more vulnerable to noise. The Xmon qubit was designed to address the issue of coherence in superconducting qubits. It does this primarily by separating out different control functions so each can be tuned for optimal performance. There are three main types of superconducting qubits: charge qubits, phase qubits, and flux qubits. The charge qubit was modified to create the transmon qubit, which was subsequently modified to make our Xmon qubit. We discussed these charge qubits in class, but I'll recap the features that are important to understanding them. Charge qubits are controlled by three important factors: the charging energy, EC, the gate charge, Ng, and the energy of the Josephson junction, EJ. The resulting Hamiltonian creates a bunch of anti-crossings, which help us isolate our two-level quantum system. When we zoom into one of these crossings, we see the sweet spot, where dE dx control is approximately 0, making the charge qubit less vulnerable to noise. However, even at this sweet spot, charge qubits can't maintain long enough coherence times. Enter the transmon qubit, first proposed by Koch et al. In 2007. Here, we start increasing the ratio of EJ over EC, and as a result, those anti-crossings we saw earlier become flatter, making the transmon qubit much less vulnerable to noise than the standard charge qubit. However, there is an important trade-off here. As these curves become flatter, the anti-crossings become further apart, and the solutions begin to look like the simple harmonic oscillator. There is a trade-off between dispersion, how sensitive the qubit is to noise, and anharmonicity, how easy it is to isolate the quantum system. Ultimately, we see that the dispersion is much stronger than the anharmonicity. So the transmon qubit is a vast improvement over the charge qubit. Still, there are more ways we can modify the transmon qubit for better performance. One such modification is the Xmon qubit, the topic of this video. Behrens et al. First proposed the Xmon qubit in 2013, which improves coherence by separating out control functions so each can individually be tuned and optimized. The device has 4 branches organized in an X shape, hence the name. The bottom branch contains the qubit, which is inductively coupled to the Z control. The other 3 connections are made with a coupling capacitor, the left containing the XY control, the top for readout, and the right for coupling to other qubits. At the center is the qubit capacitor, made from 2 intersecting coplanar waveguides. The circuit is electrically equivalent to a grounded transmon qubit. Behrens et al. Also made some improvements in terms of material deposition. With such small signals, any tiny defect in a material can lead to decreases in fidelity. To combat this, they used molecular beam epitaxy to deposit high-quality aluminum, a coplanar waveguide to minimize radiative loss, and embedded a ground plane. The combination of these improvements paid off, and Behrens et al. Found T1 up to 44 microseconds. In addition, T2 star was found to be 15 microseconds, and T2 20 microseconds. This was a clear improvement over the typical transmon qubits at the time, which were reported to have a T1 of 9.7 microseconds and T2 of 10 microseconds. Fidelity was only about 70 to 85% for this experiment, but we will see shortly how this was improved upon. In the following year, 2014, Behrens et al. Created a quantum processor consisting of 5 Xmon qubits. As you can see from the circuit diagram, they are coupled together in a one-dimensional array. As before, they have different arms for the XY control, Z control, and readout. This experiment demonstrated a set of universal quantum gates with single qubit gate fidelity equal to 99.92% and 2-qubit gate fidelity of 99.4%. This exceeds the 99% fidelity required for fault-tolerant quantum computation. They also demonstrated a 5-qubit Greenberger-Horn-Zeilinger gate using their entire processor. Generating entangled states between as many as 5 qubits opens up opportunities to perform more complex algorithms with this quantum processor. A separate experiment also showed that the states of Xmon qubits can be read out with 99% fidelity in 140 nanoseconds. These results combined demonstrate that Xmon qubits are a high-fidelity technology with accurate and fast readout, and a clear path to being scaled up. It is as simple as adding more qubits to the array to scale up the Xmon in one dimension. Behrens et al. Accomplished this in 2016 by performing digitized adiabatic quantum computing on a 9-qubit processor. Scaling up a two-dimensional array is a bit more complicated and will require more research, but ideally, the Xmon qubit has 4 arms that can be coupled to its 4 nearest neighbors. The qubits would lie in one plane on the chip, and control and readout would be handled on a separate plane. This becomes a more difficult problem because we need to preserve high coherence and gate fidelity without reducing the addressability of individual qubits. Certain microfabrication techniques are lacking to pull off this architecture, but it is expected that these will improve over the course of development. Comparing the Xmon qubit to some other superconducting qubits, we can see the many advantages. This data is from 2017, so some of these numbers may be out of date at the time of this video, but this was the most comprehensive comparison I could find. Though all these different qubits meet the DiVincenzo criteria, the Xmon has been demonstrated with the largest number of qubits. The Xmon also has the highest fidelity for both 1 and 2 qubit gates. The only architectures that beat the Xmon in coherence times are the 3D transmons and fluxonium qubits. 3D transmons are similar to the two-dimensional variety, but the key difference is that they live primarily in a 3D cavity resonator. As reflected in the table, coherence times are what these qubits are primarily known for, but some of their other characteristics are not as strong as the Xmon architecture. Fluxonium qubits are another architecture worth talking about. They contain a small Josephson junction that is shunted by a large array of more Josephson junctions. They have very small capacitances, which limits the fluctuation in charge, leading to longer coherence. T1 for fluxonium qubits is much higher than other superconducting qubits, but this has only been demonstrated as a single qubit, so there's much more work to do in terms of scaling. So where do we go from here? First, as pointed out in Behrens et al., the limit of T2 is 2T1, which the Xmon qubit is nowhere near. This is evidence that there is additional dephasing that needs to be investigated and controlled. Despite the relative performance of the Xmon qubit, decoherence in superconducting qubits is still an important area of research. Since Behrens et al. Proposed the Xmon qubit in 2013, there hasn't been much improvement in this area. One interesting proposal, however, is to replace the commonly used niobium with a tantalum superconductor. Place et al. Did this with 17 different transmon qubit architectures, including Xmon qubits, and found some of the coherence times to even exceed 0.3 milliseconds. New fabrication techniques or material swaps represent possible avenues to higher coherence. Another interesting tweak on the Xmon qubit is the Xmon qubit. The essential structure is the same, but the Xmon adds an extra layer of tunability by using a coupling factor G, which can change how strongly two qubits are coupled to each other. Dynamic coupling improves the fidelity of one-qubit operations because they can be better isolated from other qubits. Being able to turn coupling on and off also improves the speed at which two-qubit gates can operate. A 2D Xmon qubit architecture is actually what was used in Google's demonstration of quantum supremacy a few years ago, which shows that Xmons, and by extension Xmons, are some of the most mature qubits we have developed today. There is still a long way to go before quantum computers are widely useful and available, but right now Xmon qubits seem like they could be a strong contender. That's all I have for this presentation. I've listed my references on this slide in case you are interested in doing further reading. I hope you learned something new about Xmon qubits. Thank you so much for watching.